This video covers BJT internal capacitances and the high-frequency model, focusing on section 5.8. Transistor models often assume instantaneous action. However, actual transistors exhibit charge storage phenomena that limit their speed and frequency of operation. By adding capacitances, we account for charge storage, creating an augmented, frequency-dependent model. This helps predict frequency-dependent gain and time delays in circuits. The base charging or diffusion capacitance, CDE, arises from minority carrier charge stored in the base region when the BJT is in active or saturation modes. The stored base charge Qn is proportional to the collector current IC through the forward base transit time, tau f, as shown in equation 5.150. The forward base transit time, tau f, is the average time an electron spends crossing the base region. Typical values range from 10 picoseconds to 100 picoseconds. The small signal diffusion capacitance, CDE, is derived from the nonlinear capacitive effect of charge storage. It can be expressed as the product of the transit time and the transconductance, GM. Next, we examine the base emitter junction capacitance, CJE. This is the depletion layer capacitance derived from PN junction theory. CJE is defined by equation 5.154, involving the zero voltage capacitance, built-in voltage, and grading coefficient. For a forward-biased base emitter junction, CJE is approximately twice the zero voltage capacitance. The collector base junction capacitance, Cmu, is the depletion capacitance of the reverse-biased collector base junction in the active mode. Its formula is given by equation 5.156. The high-frequency hybrid pi model incorporates these capacitive effects, C pi and C mu, along with the base resistance, Rx, which models the resistance of the base region. C pi is the sum of diffusion and junction capacitances, typically few pf to tens of pf. C mu is smaller, a fraction of pf to a few pf. Base resistance, Rx, is usually tens of ohms. The cutoff frequency is derived from the behavior of beta, or HFE, versus frequency. The graph shows the roll-off starting at the beta cutoff frequency, eta v. Analyzing the high-frequency hybrid pi model allows us to derive the equation for the current gain HFE, which is approximated for frequencies where the term SC mu is negligible compared to GM. The cutoff frequency OVB is defined by the capacitances and resistance. The unity gain bandwidth, or transition frequency, omega t, is defined by the ratio of transconductance and total capacitance. This plot visualizes the high-frequency roll-off of the current gain. The 3 decibel frequency, F beta, marks the start of the roll-off, and the unity gain frequency, Ft, is where the gain drops to unity. The unity gain bandwidth, Ft, is the frequency at which the short-circuit current gain drops to unity. It is a fundamental figure of merit, determined by the transistor's transconductance and internal capacitances. Fort is dependent on bias current. It is relatively constant in the mid-current region, where GM and CDE are proportional to IC, but rolls off at low and high currents. In summary, key elements of the high-frequency BJT model are the internal capacitances C pi and C mu, and the base resistance Rx. Key parameters include the forward base transit time tau f and the unity gain bandwidth Ft.